we're now going to move into the Bohr model of an atom. This is kind of where everything comes together. And it's going to seem tough, I think, for a few minutes, but just bear with me. So we know that at the beginning, the nuclear model of the atom was that we had, very basically, we had our atom, and in it we have a nucleus, and in that nucleus we have our protons and our neutrons, and then outside the nucleus we have our electrons. It doesn't really talk, I mean, that doesn't tell us much about energy, how energy is lost or gained, or structural changes. So Bohr developed a model to try and show what's happening energetically in our atom, just kind of all based on these electrons. Bohr's idea was that the energy of an atom was quantized, and that is the amount of energy in the atom is related to the electron's position in the atom. It's kind of where that quantum word comes from. So it means that the atom can only have very specific amounts of energy. Just true, and that's going to be true for individual types of atoms. Okay, and we'll talk about that more in a minute. In his model, he says that electrons travel in orbits that are fixed distance from the nucleus. That's what we call a stationary state. So what he's saying there, let's go back again to my atom, here's my nucleus. It's saying that, let's say I have an electron here, that this electron is going to stay in a certain area. Okay, it's still moving, but it's saying it's going to stay in a certain area that has a fixed distance to the nucleus. So there could be one electron there, there could be one that's even closer to the nucleus. So our electrons are going to be in a stationary state. Stationary is not the right word in terms of, because they are still moving. It's just they're going to be in one area of the outside of the nucleus. With that being said, what we'll learn is that the energy of the electron is proportional to the distance from the nucleus. And what you're going to find is that the closer the electron is to the nucleus, the lower the energy. And that makes sense, right? Because how is your nucleus charged? It's positive. So the electrons are naturally attracted to the nucleus because of that positive negative interaction. So it wants to go, that electron wants to go near the nucleus. So it's going to take energy to keep it further away. We'll look at this here in just a second, but electrons emit radiation or energy when they go from one area to another. So let's look at this example. And this is a good drawing to make better sense. All right, so let's say, here's my nucleus. Okay, this is an atom that we've broken up into sections. So these sections can hold electrons. We'll talk about exactly what these sections are here in a few minutes. But each line represents what we call a different orbit. So it's a different area of space that we can find our electrons. So if I have an electron here versus one here, this one is going to be lower in energy because it's closer to the nucleus. This one's going to be higher in energy because it's going to take more energy to keep it away from the nucleus. Now, if I have, let's say, another electron here, if I take this electron, and I can do this, I can put it up into this one. Now it's going to take energy to do that, right? It's actually going to take continuous energy to do that because you're going to have to feed it energy for it to go further away from the nucleus. Well, the moment you stop feeding it that energy, it's going to come right back down here because it's going to want to go to its more stable state. So let's pretend these two are equal. Then once it comes right back down here, all that energy that it took to get up here is now going to be released. And that's what it means by releases radiation. So it's going to release energy out into the environment of which it's in. Okay. Okay, so I'm going to skip a few slides here since we're showing the Bohr model of the atom. All right, so I wonder if this will let me add a slide. Okay, so here's what we're going to do. I want you guys all to draw this. So I'm going to take a big atom. Okay. I'm going to put a nucleus. So go ahead and draw your nucleus. And then I'm going to break it up into, I'm going to put 4 rings here. Okay, so I'm sure yours looks better. We are going to use what we call quantum numbers to show where our electrons are. We're going to talk about each area of space here, okay? And as we talk about this area of space, we're going to give it some names. Now, we can have an idea of where our electrons are, and we can show that using what are called quantum numbers. So I encourage you to write this down if you don't have it printed out. There are 4 quantum numbers. Okay, the 4 are, the first one is the principal quantum number. It has a symbol of N. It's the energy level, but we're also going to refer to it as the shell number. Okay? Now, we're basically going to focus on 4 shells. So shell number 1 would have N equals 1. So I want you to go ahead and write here, this is going to be your first shell, or your first energy level. Here, going away from it, this is going to be your second shell, and your third shell. And then we'll look at shell 4. Okay, now what does this mean before we move on? The shell numbers, the one closest to the nucleus is your shell number 1. And then as you get away from the nucleus in these given areas, you're going to increase in your shell number. As you increase in your shell number, you're going to increase in energy. The reason being is because an electron in shell number 1 versus shell number 3 is going to be it's going to have higher energy because it takes energy to keep it away from the nucleus because of that opposites attract. Okay, so what to write down: as you increase your shell number, you're getting further away from the nucleus, and you're increasing the energy of the electrons in those shells. Okay. Then we have our second quantum number is called the angular momentum quantum number, and it has a symbol of a cursive L. This is your orbital type. We're also going to call it a subshell. So this is going to tell us what subshell we're talking about. A subshell is our shells broken up into subshells. So shell number 1, there's the opportunity that it could be broken up into more than one subshell. Shell number 2, same. Shell number 3, shell number 4, the same. And we'll go through those here in a minute. And then we're going to come back to these 2. But the magnetic quantum number, M with the lower subscript L, this is our orbital. So it tells us which orbital the electron is in. And this, the spin quantum number, MS, this is which way the electron is spinning. And you could think of it simply as spinning up or down. It's either going to go one way or the other. Okay. Let's start with our shell number, the principal quantum number. So this is, again, just where in this big atom. So again, we're only going to look at 4 of them. So 1, I'm drawing this more terribly than the other one. Okay, this characterizes the energy of the electron in a bigger scheme. N can only be a whole number. It determines the overall size and the energy of the orbital. So the larger the n, remember if n equals 1 versus n equals 2, the larger the n, the more energy the orbital has. And that's simply, again, because it's further away from the nucleus. All right, we're actually not going to worry about numbers here. All right, this is just showing you like an energy diagram. If you look, energy is increasing, and where n equals 1, n equals 2, n equals 3. So as we go up, we get more and more energy. Here's just showing you where visible light comes in these shell numbers. Okay, I'm actually going to go back to last one. Let's see if we saw that. Okay, so back to this, or we're going to go here. All right, so L. L is going to be our subshell. So L, we're going to talk about as our subshell. Before I give you the why, I'm going to tell you the what. We are going to work with 4 different subshells. We're going to work with the S subshell, the P subshell, the D subshell, and the F subshell. If we're talking about the S subshell, then L is equal to 0. If we're talking about the P subshell, L is equal to 1. D, L is equal to 2. And F, L is equal to 3. So this is just giving a numerical value to the type of subshell. You should have that memorized. Now, I'm going to add to this. We'll talk about shapes of our orbitals later, but not all of our shells have all 4 subshells. All of our shells have different numbers of subshells. The number of subshells that are possible is going to be, so L can be anything from 0 to n minus 1. N is our shell number. Okay, so what does that mean for shell number 1? For shell number 1, we'll kind of make a different column here. For shell number 1, the only value for L I can have is 0, right? Because it's 0 through n minus 1. If n equals 1, then n minus 1 is 0. Does that make sense? For shell number 2, the values that I can have for L is going to be 0. And then if n equals 2, 2 minus 1 is 1. So it'd be 0 through 1. In shell number 3, L can be 0, 1, 2. And in shell number 4, L can be 0, 1, 2, 3. Okay, so what is this telling us? This is telling me in our first shell, the one that's closest to the nucleus, it is broken up into one subshell. And that one subshell is S. So I'm just going to put a little S over this. In shell number 2, I have two subshells. I have S, and when L equals 1, it's P. So the S subshell, and the P subshell are found in shell number 2. In shell number 3, I have S, P, and D. And then 4, I have S, P, D, and F. So you can see too, as our shell numbers increase, the size of our shells is increasing because we're increasing the number of subshells that we have. And really, a subshell is just like, if you take a piece of pie, in this case, you wouldn't cut it at all. In shell number 2, you cut it in 2 pieces. One would be S, one would be P. So it's just breaking up that area of space into however many subshells are found in the given shell. Now, I'm going to add one more thing here. So when we're talking about the S subshell, so the max electrons, I want you to go ahead and write this down and we'll come back to this. But the max electrons that can be found in the S subshell is 2. The max electrons that can be found in the P subshell is 6. The D subshell is 10, and the F subshell is 14. Okay. All right. Now let's talk about the magnetic quantum number, or ML. So we've done N, our shell number, or principal quantum number. Then L, angular momentum, or our subshell. And then now we're going to look at the magnetic quantum number, which I refer to the orbitals. Okay. This number is just, it's another number, but it specifies which orbital the electron is in. All right, so we're going to go back here to our chart. I'm sorry that I'm being redundant here, but it will help make more sense. So I'm going to write my shells here. All right, these are shells 1, 2, 3, and 4. So I'm going to put here our L values can be, in this case, 0, 0, 1, 0, 1, 2, 0, 1, 2, 3. So that is the same thing as S, S and P, S, P, D, S, P, D, and F. Sorry about that terrible handwriting. Okay, that's what we know so far. Now we're going to look at, so this is our bigger space. I'll actually look at shell number 2. Shell number 2 is our bigger space. It's broken up into 2 subshells, the F subshell and the P subshell. Now the subshells are broken up into orbitals, and that is your ML. So they're broken up even further into orbitals. Now ML can be an integer of negative L to positive L. So if I'm talking about L equals 0, then ML can only be 0. Okay. If L equals 1, or the P subshell, ML can be -1, 0, +1. If L equals 2, or the D subshell, ML can be -2, -1, 0, +1, +2, and then when L equals 3, ML can be -3, -2, -1, 0, 1, 2, 3. Okay, so what does this mean? This means if I'm talking about shell number, or if I'm talking about shell number 1, and it has one subshell, it has the S subshell. That S subshell only has one orbital. And this number is really arbitrary. I mean, every integer represents a single orbital. So shell number 1, when I have a P subshell, the P subshell is broken up into 3 orbitals. The D subshell is broken up into 1, 2, 3, 4, 5 orbitals. And then the F subshell is broken up into 7 orbitals. And each one of these numbers just shows a particular orbital. Okay. Now, remember I said that when you're talking about the S subshell, it maxes at 2 electrons. The P subshell maxes at 6. D is 10. And F is 14. Okay, so that's for the subshells, right? So all the electrons that fit in these should add up to be 6. Now, here's the thing. For every ML value, there only fits 2 electrons. Every orbital only fits 2 electrons. So the S subshell has 1 orbital, and there's 2 electrons in there. That gives us a total of 2. The P subshell can fit 6, so I should have 3 orbitals. Each one of them has 2 electrons in it. D has 10 electrons total. It's broken up into 5 orbitals. 5 times 2 is 10. And then F, 14 electrons, broken up into 7 orbitals. 7 times 2 is 14. So the numbers are starting to work. And that's why we have the numbers that we have here. Okay. Now, in each orbital, so let's say, I mean, it doesn't matter what value I take. Let's just say we're talking ML equals 0. So we're talking about that orbital. Each orbital holds 2 electrons. Okay, out of those 2 electrons, one of them is going to spin one way, and one of them is going to spin the opposite way. So that's why this is called the spin quantum number. Each one of my arrows here represents the electron. They're not going to spin in the same direction because that wouldn't be energetically favorable. They're going to spin opposite directions in order to sort of balance that out. But the spin quantum number describes which way the electron is spinning in an orbital. Now, we do assign a value for this, and that is that one of them is spinning 1/2, +1/2, and the other is spinning -1/2. So that would be like here. Let's say this is +1/2 and -1/2. So that's going to be true for every single given orbital. So every orbital is going to have an MS value of positive 1/2 and an ms value of negative 1/2. All right, so let's go back. Let's see if I can go back. Well, let's see. All right, now we're gonna kind of put it all together. We're gonna describe in an orbital. We describe one orbital. It's gonna have its own NL and ML values. Okay, and then if we're talking about each electron in the orbital, N, L, and ML will be the same, but your MS will be different. Okay, now we're going to talk about energy real quick. So all the orbitals that are in the same shell or have the same N value, they have the same principal energy level. So we call it, that just goes with our shell number. And then the same will be true, the orbitals that fall within the same subshell or L value, they're going to have the same energy value. Let's look at an example of this. All right. So here we're just going up in shell numbers, so kind of pretend that your nucleus is right here, and we're just going up. These would be our lines. Okay, so follow with me here. In shell number 1, we know we have the S subshell, or L equals 0. And we know in that subshell, it can only fit 2 electrons. Right? There's only one subshell. S subshells can only have 2 electrons, which means there's only one orbital. And we know that because we have only one ML value right here. So that in that orbital, this little box here is for me to show those 2 electrons. And I'm going to show them with arrows. So we've got one going up and one going down. All right, so here, this is something you should add. So the max number of electrons that can fit in shell number 1 is 2 total. Okay, so let's move to shell number 2. Shell number 2 is broken up into 2 subshells, the S subshell and the P subshell. Okay, I know that because it's 0 through n minus 1. The S subshell we know only holds 2 electrons. It doesn't matter that it's 2s or 1s. The 1 here, by the way, is just because it's shell number 1. The 2s here is because it's shell number 2. And then we know that the P subshell, all P subshells, doesn't matter what shell it's in, it holds 6 electrons. And the 2s will have 2 electrons that will fit in this box in one orbital. In the P subshell, we're going to have 3 orbitals, and I see that here, where ML is -1, 0, and +1. So in each one of these, we can fit 2 electrons in each, giving us a total of 6. So how many max electrons can fit in shell number 2 total? It includes all of these, so it would be 8. Okay, shell number 3, we know is broken up into 3 subshells, the S, P, and D. S has 2 electrons, 1 subshell. P has 6 electrons. D has 10. Okay. One orbital houses its 2 electrons. 3 orbitals houses the 6. 5 orbitals houses the 10. So how many total electrons can fit in shell number 3? Be 18. And now we know better where those 18 electrons can be in regards to shells, subshells, and orbitals. Okay. If we had n equals 4, n equals 4 has L equals 0, L equals 1, L equals 2, L equals 3. Okay. So L equals 0, that's 2 electrons, the S subshell. L equals 1, 6 P. L equals 2 is the D subshell, it's 10. L equals 3 is the F subshell. Oops. Sorry, let me do that. So this is new, it's our F. Okay, it incorporates all of those. I'm not going to write all the ML values out. You have it for here. ML would be 0. ML would be -1, 0, +1, -2, -1, 0, +1, +2. And then here it would be -3, -2, -1, 0, +1, +2, +3. So total for shell number 4, how many electrons would I have? 32. So that's the max. So that means shell number 1 I can fit 2. We know where they're broken up. Shell number 2 I can fit 8. We know how they're broken up, etc. Okay. Talking about energy levels here. We know that shell number 1 to 2 increases in energy. So because it's getting further away from the nucleus. So the larger the shell number, the more energetic. Now for our subshells, S is the least. So it goes S, P, D, and F. So that means eventually here, when we start filling shells, we're going to fill the S first because it's the least energetic. So this is increasing energy. And we always fill, and what I mean by fill is we always put our electrons first in the least energetic places. So we'll start with shell number 1, then we'll go to shell number 2, but we'll start with the S subshell, then the P subshell, etc. Okay, I'm going to come back in a different little voiceover and do a lot more with this. But before, we're just going to look at the shapes. This isn't totally important for you to have memorized, but you should be able to identify the shape of some of our subshells. But in just to sum up what we just did, the number of sublevels in general, the following are true. The number of sublevels is whatever n is, or excuse me, I'm sorry, with the number of subshells, I should say, this was misprinted, is 0 through n minus 1. So we'll come back to this. Here's where I just want to show you, okay, our S subshell, or S orbital, where L equals 1. This is, like, pretend this is your nucleus. This is the 1s. It's spherical, so it's shaped like this. It's the lowest subshell in terms of energy, and it just kind of looks like this. So somewhere in here, this is where you're going to find your electron, the space. When I have a p subshell, I have 3 p orbitals, right? So that's when L equals 1. So ML's -1, 0, and +1. So these are 3 areas of space in the p subshell, right? And I'll show you what they look like. So here, this would be one of them. You're going to find it, they kind of make the infinity sign. So you're going to have one on the x-axis, one on the y, and one on the z. So those are 3 different areas of space that you're going to find an electron. Now you'll notice that when they come together, there's like 0 spot. That's called a node. In the node, you'll never find an electron. It's going to be within the bubbles that you see there. Okay, then when L equals 2, it's our D subshell. Our D subshell has 5 orbitals. So there's 5 areas of space that you'll find your electrons, and that looks something like this. So each one of these represents an orbital or an area of space where you'll find the electrons. And then lastly, the F subshell, where L equals 2. I have 7 F orbitals, so that is 7 orbitals or areas of space. And this is what they look like. So basically, those are the shapes. So we're going to take a break, and then we're going to do some work with those quantum numbers to make it even better.